Welcome back. We're going to pick up where we left off last time. And we've been learning about the kinetic theory and how the movement of the particles affects the state of matter. So we had finished up and I had asked you to answer these questions on your own. A solid turns to a liquid because of increased heat. So, I mean, that should be pretty obvious. You have a solid like ice, you increase the heat, it melts and turns into a liquid. The heat of vaporization is required to turn a liquid to a gas. And the way you can remember that is a gas is a vapor. In the gas phase, the molecules are farther apart than they are in the solid phase. They're free to move. All the bonds have been completely broken. And so the gas is free to move and expand into whatever space it's in. What is thermal expansion? When heated, the molecules in a substance vibrate faster and faster, which means they are moving around and take up more space. As they take up more space, the substance expands. So when it's cold, the molecules are barely moving, they're not moving a whole lot. As we heat it, they start to move faster, 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 faster. You can imagine my hands are like the molecules. As they move faster, they start spreading farther and farther apart. And as they move faster and spread farther apart, that's what causes the substance to expand. There's a little video clip that I want us to look at. Okay, so this is a short video I wanted to share with you to review thermal expansion. You can see as they heat up this substance, the particles are moving faster and faster. And as they're moving faster and faster, they're vibrating farther and farther away from each other. As they vibrate farther and farther away from each other, they're taking up more space. That's why it expands. Okay? The particles have more energy as they're heated. They're vibrating farther and farther. Now remember our model. We said the particles were hooked together, and we think of it like a spring. So as the particle is heated, okay, it's moving farther and farther out here. So as it moves farther and farther out, with more heat, it is expanding. Okay, so as it heats, okay, it spreads farther and farther away. Now, eventually, what's going to cause phase change is it's going to break so far out here that that spring actually breaks. Okay? What is changing from one state of matter to another called is called a phase change or a change of state, which is what this unit has been on. Sometimes you'll hear both of those used. Sometimes they'll say this is a phase change, or sometimes they'll say it's a change of state. So it's going from the solid state to the liquid state, or from solid phase to liquid phase. What stays the same during phase change? Temperature. As those bonds that we've been imagining are there in between the particles break apart, instead of the temperature going up, the increased thermal energy is actually going to break those bonds, and the temperature phase change. So often you'll see, like when snow is melting outside, no matter what would be happening, if you stuck a thermometer in the snow, it would be at 0 degrees Celsius. Or when water is boiling on a stove, for example, it always boils at 100 degrees Celsius, the temperature does not rise. Okay, now we're going to have a quiz on this phase change graph. So we had looked at this last time, but we need to go over this and review this again. Okay, so we have increased heat, so we're heating this substance. And the reason why they use time for heat is, let's say that we had this substance, it shows water, in a container. And we had it on the stove, and the burner put out a certain amount of heat every minute that it was on. It's easier to measure the time passing than it is to measure the actual heat coming out of the burner. But if we get it, like, and we have it on at medium setting, and we just leave it at medium setting, Well, the heat that it lets out is going to be pretty consistent as time passes. So a lot of times when people do these experiments, they measure the time passed, okay? But that's equal to the increasing heat as the burner lets out heat. And then we're going to have a thermometer in the substance and be measuring what happens to the temperature as time passes and it changes phase. Right? So whenever you're asked graphing questions, you always need to be very careful to look what's plotted on the different axes. On the x-axis is heat, and on the y-axis in this graph is temperature. Now, if they ask you a question about temperature, okay, so along line A for temperature starts right here and it ends here. This is the temperature segment of line A. The heat part of line B starts right here at 0 and it goes to about 2.5. So this is the part where line A is the heat. So we have the part of line A that's represented on the x-axis and the part of line A that's represented on the y-axis. Now for line B, this is line B on the x-axis. But when we look at line B on the y-axis, it's just one point. Okay, so what it's showing us is that during the time that the substance is being heated, no matter what point in time or as the heat increases, line B always stays the same. It stays at 0. Now, the part of the line that's represented by C on the x-axis starts here and it ends here. This is line C on the x-axis. On the y-axis, on the y-axis, this is line C. So line C starts here and it goes up to here on the y-axis. And line C starts here and it ends here on the x-axis. So the heat increases from about 4 to 9, and on the y-axis, the temperature increases from 0 to 100. On the x-axis, this part represents line D. Okay, so the heat for line D starts at about 9 and ends at about 13. On the y-axis, D is only 1 point. Okay, it's right here. And then line E begins here and it just continues on. So this part, going out to infinity is line E on the x-axis. And on the y-axis, line E goes on up. Okay, so when we're looking at the graph, okay, and we're answering graphing questions, it's very important that you look at what's being plotted on the various axes. Okay, so what's happening to the temperature along line A? Well, we're going to look at the y-axis to find out the temperature. Along line A, the temperature starts at -20 and it goes to 0. So from -20 to 0, it's a solid, and the temperature would be increasing. Along line C, it shows that the substance is a liquid. So the temperature of this solid, it was really cold, and it rose to this temperature here. During melting along line B, the temperature stayed the same, and then it was a very cold liquid, and the liquid heated up until it got to point line D. This would be the boiling point. And then it boiled away, and we have this vapor, this gas along line E. So along line B right here, we have melting and freezing. Sometimes that's called fusion. The particles fuse together as they become a solid. And along line D, we have vaporization or boiling. Notice that during both of these phase changes, the temperature stays constant. At the beginning of line D and at the end of line D, we have the same temperature, and the same thing for line B. The energy needed to melt the solid and turn the solid to a liquid is called the heat of fusion. The energy necessary to vaporize this liquid or turn the liquid from a liquid to a gas is called the heat of vaporization. So that's how much heat had to be added from 9 to about 12 and a half or a little more. Okay, that amount of heat is what it took to vaporize this gas. And same thing with the heat of fusion, from about 2.5 to 4 is the energy that was necessary to turn the solid into a liquid. Okay. And as I said before, the temperature stays the same during phase change. So what I'm showing you here is at the beginning of line B, we follow this green line over to the y-axis and the temperature is 0. And a little while later, we go up to the y-axis and we follow the temperature over and it's still 0. So the heat is increasing. Okay, it's taking energy to melt this solid. The temperature is staying the same. Same thing happens while this water is boiling. Okay? Somebody said, well, when the heat was at 10 units of heat, or the time was 10 here, we go up, and what's the temperature? It's 100. A little while later, the heat is still on, the heat is increased, the time the burner's been on has gone up. We look over here, and the temperature is still 100. So during this time of phase change, the temperature does not change. And this is one of the reasons why cooking with water and boiling things is so useful. Because once the water on the stove reaches the boiling point, you don't need to worry about the water getting any hotter. It just stays there at that boiling point, which is 100 degrees. And the melting point of this solid is at 0. So really, really cold ice could warm to 0 degrees. During the time it melts, it stays 0. And then it's this really cold liquid, which is going to warm until it gets to 100 degrees, and it will boil. And the liquid will vaporize, and it becomes a gas, and then the gas can get hotter and hotter. Okay, so what's happening to the temperature along line A? Well, along line A, the temperature goes from -20 to 0, so it's increasing. What's happening to the heat along line A? Well, along line A, the heat goes from 0, and we said to about 2.5. So 0 to 2.5 is increasing. And the state of the material along line A is a solid. It's in the solid state. Now it's going to ask us about line B. What's happening to the temperature along line B? Well, along line B right here, as we said, okay, at the beginning of line B, it's 0. In the middle of line B, it's 0. At the end of line B, it's 0. So the temperature remains the same. What happens to the heat along line B? Well, the heat is on, okay, and it's increasing. It's going from 2.5 to about 4. What's the name of the heat that's necessary to melt the solid and turn it from a solid to a liquid? The heat that starts here from about 2.5 to 4 is called the heat of fusion. And this has described the nature of the material along line B. Well, if you think about at home or outside on a snow day, when the snow is melting or an ice cube is melting, you have the solid, which is ice, but you also have some liquid. So during that phase change, you have both phases. You have the previous phase and the phase that it's going to. So the nature of the material along line B would be a solid and a liquid. You still have a solid ice cube, but you also have a puddle of water around it where it's melting. And next it asks us about line C. So when it asks us about line C, we're going to look down to the x-axis here. As we said, line C goes from about 4 to about 9. And on the y-axis, line C goes from 0 to 100. So what happens to the temperature along line C? Well, it goes from 0 to 100, so it's increasing. What happens to the heat along line C? Well, along line C, we're going to look down to the x-axis. And line C starts at about 4, and line C ends at about 9, so that's an increase. It will be increasing. And what's the nature of the material along line C? We said it's a liquid. It's a cold liquid, and it's going to warm and become. It's going to warm until it gets to the boiling point. Finally, it's asking us about line D. Line D on the x-axis starts at 9 and it ends at about 13. And on the y-axis, it stays right at 100. So what's happening to the temperature along line D? It remains the same. As we said during the whole time, a liquid is vaporizing, it stays at a constant temperature. What happens to the heat along line D? It increases. Line D starts here at about 9 and it goes to 13. And the name of that heat is the heat of vaporization. Now, what is the nature of that material? Well, if you think about a pan of water on the stove boiling, there's liquid in the pan, and there's the steam and the water vapor above the pan. So during that phase change, like we said before, we have the previous phase, the liquid. We have also present phase that is going to gas. And we're going to stop here and pick up again next time. And I hope you're having a great day.